I'm a little concerned now because you guys are still there, I guess. Sorry. I'm a little concerned. I think the motherboard's going out on this. Man, these Apple MacBook Pros, I spent a ton of money on them, and the motherboard's gone out now on 2 of them. Now I think this motherboard's going out. That's about a $700 fix. So what happens is you're going along, it just dies. If it happens here, you guys are cool. You'll hang out. But if it happens, I'm running the show tonight. Now I'm freaked that tonight on Ask Me Tutoring, it's going to just die on me. Okay. So you guys say hello. Are you here?
Yeah, we're here.
Okay. Sorry about that. So if that ever happens, just be patient. You know, I'm frantically trying to get back on. So did you hear me talk about the stadium and going to the stadium? Oh, let me share the screen again. Takak, did you hear that?
Yeah.
Okay. So let me share again. So I don't know. I wasn't looking, and then I looked up. It was gone. So now we're trying to share a screen again. Maybe that's what throws it off. Okay. So we lost all that recording, but it's no big deal. Well, hold on. Now I can't get it to share. This is acting really wacky. There we go. Okay. Man. All right. So this is the weather coming up this week. Like I said, we'll be zooming since a new recording now because we just lost it. A couple of things I talked about. Chuck Yeager died last night. We talked about him being an American hero, but that got lost. And then we're zooming tomorrow, but it's tomorrow night from 9 to 10. And then Thursday, we're going to the stadium. You guys feel free to come to the stadium with us. I'd probably, it's an outdoor activity, but I'd probably get there. It's a fun thing that we do. We just drop in basketballs and tennis balls and timing it. And we're trying to see if we can get that, how close we can get to G. We know it's 9.81, but let's check for ourselves, right? There's a phrase called nullius in verba, which is Latin, and it means not by word of mouth. And this phrase is painted above my doorway at Norman High School. It is the original phrase of the Royal Society, which was the think tank. Isaac Newton was the head guy there, Robert Hooke, all these guys with the Royal Society. And that was their phrase because up until those 1600s, science was like Aristotle. Nobody got their hands dirty. You just until Galileo started rolling balls down ramps. No scientists really out except for astronomers, but even they didn't actually do a manipulating experiment. So anyway, it's called nullius in verba, which means not by word of mouth. And so sometimes we want to verify something. I don't want you just take my word for it that G is 9.81. Let's go do some kinematics. Let's drop some basketballs and tennis balls and stuff from the stadium. It's fun, but it's going to be a little cold tomorrow. It's Thursday morning. So if you want to come out, just you can hang out at the stadium and then we'll head over there. I'll give you more details tomorrow night. Okay. And the other thing, since we just came on air here, I'm not going to talk about it, but that is Chuck Yeager. There's Chuck Yeager. He died last night at the age. He's the first man to break the sound barrier. Died last night at the age of about 94, I think. Well, in class today, I did a homework check. Now, remember, your homework check for 212, that is due for you tonight. You got to submit it. Your virtual students have to submit it. They come along, I give them stamps in class, but you have to submit the paper. Okay, so you submit the paper tonight through Canvas, and I'll give you those 20 points. This is 212, you're submitting. Okay. We did 211 in class. Well, we did it in here yesterday. We did 6A anyway. You all for homework were supposed to do 6B. And what did I have them do? Did I have them do anything? No, I just checked it. We didn't really talk about 6B at all. We did say this much on 6B, how many seconds. So you can use the For that one, you can use the first orange, V final equals V naught plus AT. V naught of those planes are 0, so time is simply V final over A. And so let's throw the givens in there. So V final, we found, well, it says V final is going to be 140 knots. So we have 140 knots, Kn over 1. That's my V final. And then the 1 over A would be 175 kilometers per hour under our dot minutes. Yeah. Okay. And then you can do the rest. You're going to end up with seconds. Okay. All right. Now, so we did that. We looked it over. For the black and blue, number 1's black. Number 6 is blue. Number 7, D, is black. Tomorrow, this afternoon. Now that will, I'll probably do that tonight after the after AMT. I'll probably do that, and then I'll just have it scheduled to be released tomorrow at like 4. I want you to first try these on your own. I don't want students just to go right to the video key and just copy down the answer. I'd rather you try it first. Now, Eric asked about 9, and so 9A, 9B, and then we have, it was in this area, this class that we talked about 9A and 9B more than the other classes. But that was everybody agrees that's probably the best way to solve 9A. But on 9B, I found 3 ways to solve it. So in, justifying my 105 meters as my answer, because I noticed that some people were getting 38 or something like that. And the reason is that they were probably using, my guess is, if you're having trouble in that problem, you were probably using maybe the wrong velocity there, because it says how many meters does the car travel. So I'm trying to find V naught. And if you plug in V final, here, you'll get the wrong answer, right? You've got to plug in 157 kilometers per hour. And then when you plug all that in, you get 105, which is correct. But then I worked it another way, which I claimed to be easier. But now that I'm working it, now that I worked it, I thought, well, that's only not that much easier. It's probably about the same. So that's my method. And then I said, there's really a third method, and that's graphically. So this is the graphical way of solving that. And I thought this was interesting. It's using the trio. We know that acceleration is -7 meters per second. And then we know that velocity, that's the slope of the velocity. So you can see that your velocity dropped off 22.8, went down 22.8 meters per second here. But you're still trying to find out. So then I plugged that in and I got 37 meters. I thought, oh, something's wrong. But not really, because that's how much, okay. That acceleration, that negative acceleration is like a tax put on that motion. That car, or whatever this is, wants to go, it says an automobile. So that car wants to keep going because of Newton's first law of inertia. That car wants to keep going at 157 kilometers per hour. And if you did that for 3.25 seconds, you would be at 142 meters away from where you started. But you are braking. So that's like a tax on your motion. It keeps eating away at your motion. And what it does is in 3.25 seconds, it's eaten away 37 meters from what you would have had if you weren't braking. You see? So 142 minus 37 gives me the answer I'm looking for. So this one turned out to be a little bit harder than just plugging in. But I like it because it forced me anyway, while I was working it last night, it forced me to, think about the graph. I mean, that's a cool thing about physics. You can explore something for different topics, and then you see it from a different way, and it makes it all make more sense. This is important. This is not wasted time, because this is important when we get to what we're about to do, free fall and projectile motion, okay? So there's all that. We good? Questions so far? Okay, so we talked about all this today in class. And then we did this, but we've already done this. So we did, this took up a ton of class today, was this, questions and all. It was a good discussion. And this actually is on, I like this so much, it's on the take-home test. And if there's room, it's going to be on the test. The take-home test and the test are both one page, two sides. So theoretically, I could just change the numbers around and put the same problems on there. The problem is the take-home test is pretty squeezed down, and it might make it a little difficult to get it all done in 55 minutes. All right, so I'll probably have to take some problems out. Anyway, you'll see the same problem on a similar problem on the take-home test. Work the same way. Okay, so actually the bulk of the class was this 214. So we're going to work on 214. We'll start it anyway. Okay. So 214, it seems like we're breaking away from what we need to break from kinematics. And we're about to get into free fall. And then from there, we're going to put free fall, and this will now be into January. We're going to put free fall and orange. Free fall's blue. So we're going to put orange and blue together, and we're going to get projectile motion, which is, basketballs and footballs and mortar shells and golf balls. It's all projectile motion. It's sometimes called ballistics. So so but then the thing is, these are all vectors. And so that comes into play. So I thought we ought to probably talk some more vectors first before we get more into. And plus, the good thing about this is it doesn't require any calculator. Okay. No unit analysis. Yay. Okay, so here's the bad news. It does require a protractor and a ruler, which there's a real good chance you don't have one at home. We have protractors at school. We put them in the UV lights between classes, and so we're careful, but the kids all use protractors in there. All right, so you probably want to you're going to need a protractor, maybe even for this next test. So you probably want to buy a protractor, not really for the take-home, but there will be a couple of problems on vectors that aren't on the take-home that'll be on the test. I'll talk about that later. So for next week, so maybe this weekend, go buy a $1 protractor somewhere, Walmart or something. I had them for sale, but I've sold out now. Okay. So, and no, I don't make a profit. It's I sell them to you what I buy it for off Amazon. So here it says use a protractor and a ruler to describe a map view of the velocity vectors below. So since you don't have a protractor, let's do it. Let's use my protractor. So this gives me the angle, and that angle right there is 21 degrees. Another good thing about having an iPad, 22 degrees. And then you got to get the length. Oh boy. Well, I have a ruler, but I don't have a paper copy. Hold on. Let me get a paper copy here. Yeah. All right, here we go. So that I can look at yours, see what you're seeing. Mine's the scale's different, of course. So let's take a ruler now and measure the length. And then you're going to use that scale over there. Here we go. So, ruler here. And if you have a ruler, you should check it too. So this has a length of 3, close enough, 3 centimeters. Okay. So then we use that scale over here, and this scale right here. 1 centimeter equals 10 meters a second, so it's 3 centimeters. So there's a proper description. Now, proper description means if you have to text it to a friend and you don't have a camera, but you got to describe this vector through text, okay? So you would say that it is not 3 centimeters long, because we're talking velocity. You would say it is 30 meters long, meters per second long, at, and now you give the angle, 22 degrees. Well, I can't just say 22 degrees. I have to say what quadrant it's in. But you don't put 20 degrees in the third quadrant. You say 22 degrees south of west. And so someone in class said, well, why don't we just call it southwest? Why say south of west? Because if I just say southwest, I don't know whether it's 22 degrees south of west or 22 degrees west of south. So you have to be clear on this. Now that's called the proper description. Proper description. So on tests and in life, you'll be asked to give a proper description of that vector. Okay. So now we did that one. I'd say you all do this one, but you don't really have a ruler. Maybe you have a ruler, hopefully, and you don't have a protractor though, probably. So I'm going to get my protractor. I'll just help you out here. That is not what I want. Okay, so I'll go this way. Yeah. All right. That's what, okay, that's what, not to be 90. That's 0. So this is actually 14 degrees, what it has here. 13 degrees, right? Yeah, 13 degrees. So that's 13 degrees. Then take your ruler, measure that sucker. It's nice that we don't have to worry about a calculator, but it's kind of a pain in the butt. I like this kind of stuff. And let's go ahead and call it 3.5 centimeters. Okay. So then multiply that times 10. We have 35 meters per second at 13 degrees. This is a map view. We're looking down on it. So we would say south of east. Okay. Those two make sense so far? We good? You have little icons there. You hit the thumbs up button. Okay. Now, that's for a map view. But sometimes we're looking at it from the side, like looking at a basketball player, looking at the arc of the basketball coming off, or if you're militaristic, looking at a cannon or the old traditional cannon. What angle is that projectile leaving the cannon at? So that's a side view, or called a profile view. All right, so we got to find the angle again. And this is acceleration this time. So this guy is 53 degrees. So, and then the length, this time the scale is 1 centimeter equals 20 meters per second. So going back on the paper, I get 2.5 centimeters. So that's 50. meters per second squared at, so some kind of thrust at 53 degrees. But then wait a minute, I can't call that north of east. This is not a map view. This is looking at just the profile. And so in that case, we use this. So let's change this here. So in that case, we use this. For a map view, we have north of west, north of east, south of west, south of east. But for a profile view, we use this. Now, what the heck does that stand for? ALH, ARH, BLH, BRH. Anybody want to hazard a guess? What do you think? Oh, we have a couple of comments, do we? Oh, okay. Yeah, one of the lag. Oh, hey, Jacob. One of the lag. It was just the screwed up one laptop screwed up. So what do you think this ALH, ARH, BLH, BRH stands for? It tells the quadrant of a profile view.
Is it like above left of?
You right? Above left of, what's that H?
Head?
Above left of, what's this?
The horizon.
Horizon or horizontal. So we take above left horizontal, above right horizontal, below left horizontal, below left, or horizon. So that's what we, those are the, that's so the reader knows what quadrant you're in. So this, in this case, would be, that would be above right, ARH, above right horizontal, okay? You're just trying to find a way so we can all talk to each other. Now, different professors have different methods. Some would say, like for this one, that they wouldn't say that was 22 degrees. They would say that is the 202 degrees, right? That is not very descriptive. Now, when we get to work and energy, we will have to do that because of the formula. But if I'm trying to, I started off teaching that way, and it got so confusing. So it's just not how you talk, right? I mean, you talk about the reference angle. So the reference angle, we always deal with the reference angle. And depending on what professor you have in college, hopefully they also deal with it. It's just it seems like a logical way to talk about things. All right. Now do this one. This guy, this acceleration, that's a lot. That sucker is 7.5 centimeters long. So that times 20, we're doing 150. So this guy is 150 meters per second squared. And then you go, whoa, what's that? Just say left. Left. So that's like 15 Gs. Because remember, 10 Gs, 10 meters per second squared is a G. So that's approximately 15 Gs, which is crazy. A crazy amount of, that's a John Glenn kind of thing. Okay, so everybody okay? Those are the basic ways we're going to end up describing vectors. And then we fill this table out in class. We're actually getting close to being done today. We go early because we were way ahead yesterday. We may go a little, we'll stay ahead a little bit. Anyway, so here we have, we're supposed to check off whether it's a scalar or a vector. And so how about you do this? How about, let's do a little exercise. I'm going to stop the recording. And then if you're watching this and you're watching the recording of this, pause it. And I want you on that table to try and list what you think each one is. So you go ahead and do your check off. And so do that, give you a minute, and then we'll talk about it. Okay, so let me pause. Okay, so we're back. Temperature, right? Temperature is a scalar. There's no direction to temperature. So that is a scalar. Force, you're hitting something. Yeah, you got a size of the force and then the direction that you're moving. That is the quintessential vector. Volume, I got a 12-ounce bottle. No, that's just a scalar. Displacement, that's our delta x, remember? That is a vector, whereas distance, which is the length of that, is a scalar. Speed and velocity, velocity is the vector and speed is the scalar. Speed is like how fast you're going. And then we get to time. And so what do you guys think? Is time a vector or a scalar? In other words, can time be represented with an arrow?
Scalar.
Okay, so we hear both. And in classical physics, we are going to call time a scalar. But there's a guy named, okay, let me go to the next page here. Yeah, there's a guy named, squeeze it in here. There's a guy named Sean Carroll. Look him up. And Sean Carroll is I would say he's one of the top 20 thinkers alive today. He's a physics professor, Caltech, I believe, is where he's at now. But he's written some books. And one of them is called The Arrow of Time. And he's given some TED Talks and stuff. But this arrow of time, this idea, he was on a Joe Rogan podcast. And I used to watch his lectures, Sean Carroll's lectures. I like the way he talks for some reason. But check him out. But he was on Joe Rogan at JRE, and I would strongly suggest you watch this, Joe Rogan Experience. You watch this podcast either on YouTube, or YouTube's the best because they go through Wikipedia and they show pictures. If you just listen to it, you don't get all that. But anyway, so throughout the whole time, Joe Rogan's going, his brain keeps exploding on the stuff that Sean Carroll is talking about. But he's talking about the arrow of time, which makes you think that time is a vector, right? Because it's an arrow, and vectors are arrows. Well, what he means is, all right. So here's a quick story. I told the kids this. I have all these ceiling tiles in my room, and I should have taken a picture of this one. But I asked the kids. I said, I had a student named Levi Gentry, and Levi's a very bright kid. He liked to do art. He was very active, always a thinker, always in my room, pondering stuff. And now he's doing really well. But I said, Levi, he said, I'm going to paint you a ceiling tile. What do you want me to paint you? I said, why don't you paint me your version of time? And so, because I knew he'd give me something good. He thought about that for like 2 weeks. And finally, he came in with his ceiling tile he painted. And it's really cool. I wish I could show it to you. I should have a picture queued up, but it's somewhere back in mine. But on this ceiling tile, he painted this. It's orange. First, he painted it orange. Okay. Let me try and get it right. Okay, so he painted the thing orange background. Oops. All right. I won't do it justice, but he painted it orange, and then he put these black lines on it. And the black lines look like, I think this is brilliant. When I retire, I'm going to steal that. Well, steal it. I mean, I guess it's not really mine, it's the school's, but that's one ceiling tile. I'm going to take about 5 or 6 ceiling tiles. That's one of them. So on the ceiling tile, he starts off with a line. Thicken that up. Okay, there's a line here. And then as you keep going, that line starts to get a little bit like that. And then it gets more. I'm not doing it justice. He did a better job. And then it gets more. And so the line becomes more and more chaotic the further you go. And then it finally does loops and loops. And again, it gets all crazy there at the end. And so he said, that's time. And I thought that was brilliant. So if you were to show the direction of time here, what direction would it be?
Upwards.
Yes, it would be on this screen, it would be upwards. So I'll show arrow here. All right. Oh, I can't make that arrow up. Anyway, so it would be an up arrow going like this. That would be the direction of time. Now, can you tell me, what does this thing represent? What's happening as I go from the bottom to the top? You may have had, if you're in AP chemistry, you may have talked about this.
Entropy?
Exactly. Thank you. Who said that? Is that Miranda? Okay, Miranda. I figured Miranda would come up with that one. All right. So S, capital S. I put little tags on there to make sure you realize it's capital. Remember, lowercase s is just our generalized term for distance, but this is capital S. And so entropy, what entropy? Not enthalpy, entropy. And entropy is the measure of chaos. If you go down to the atomic level, it's the number of degrees of freedom that an atom can have. And when you maximize that, then you've maximized entropy. So what Sean Carroll is saying is that time is a measure of the increasing change in entropy. And so there's something called the second law of thermo. Delta S is always going to be positive. So delta S is always growing. It's always getting, like the way we know time is moving forward is things are becoming more and more chaotic. Entropy is a measure of, it's a measure of disorder. A measure of disorder, or a better way to say, a measure of chaos. And this is the second law of thermo. Okay, down here, this is better. Okay, so down here, this is what I was showing. The second law of thermodynamics, and thermodynamics is the study of heat flow, which one of the links between chemistry and physics is thermodynamics. Because, you know, in chemistry, you hold a beaker and the reaction, or say a test tube, and your hands are getting hot, and we call that exothermic. And then if you hold that test tube and you put something together and it gets cold, we call that endothermic. It's all about heat flow. Is heat flowing into the reaction or heat flowing out of the reaction? So that's a elementary version of it, but that's that's a little bit of thermodynamics. And there's Gibbs free energy and all these little equations that go with it. But entropy is this measure of chaos. And so the second law says that that must always increase. As long as chaos of the universe, I'm talking the universe now, as long as chaos of the universe is increasing, time is moving forward. Okay. So I thought that Levi's description of time was brilliant. I'm going to frame that thing one day. Okay, so yeah, so in that, so what Sean Carroll is saying is the arrow of time is always this. It's basically saying that in order for things to go forward, entropy has to increase. And it goes into all these cool things about the universe. So like you could say something like, well, we have blocks, little blocks in the room. And I say, okay, I'm going to bring order. I throw the blocks down. And then I'm going to bring order out of this. Well, didn't I just now decrease the amount of chaos? Didn't I just violate the second law of thermodynamics? This is what always bothered me in high school when I heard this. I thought I can easily organize something. Because I understood from my, I don't know, it's a chemistry teacher or something. I think I had, yeah. And she was saying this, and I was thinking, what? That's the dumbest thing I ever heard of. I can organize stuff. It's because I was under the impression she was saying you can't organize anything. And what she meant was, what I probably wasn't listening, was that you can't ultimately organize anything because so you answer that question then. So how can I, if I have, I'm going to throw out some blocks tomorrow and see if we can do this in class. So if I throw out 30 blocks and they're all scattered everywhere, and then I take them and I start putting them all together, I make a nice, like a Jenga, you know, I make a nice structure out of it. Did not I just violate the second law of thermodynamics? What do you think? Ponder, ponder, ponder.
The blocks might undo themselves eventually, and there will be more entropy.
I agree I agree what you're saying. So ultimately, you temporarily brought order to a system, but that's not what Sean Carroll's saying. He's saying that not in say it sits there for a week, then finally falls over. You go, well, see, haha. No, he's saying at the time when you finally make that nice stack of blocks, you still increase the entropy of the universe. Anybody know why? Let's take another example. Let's say that your parents are bugging you on the weekend. They said, you got to clean your room. You got to make your bed. They get all the books up, all these games. Okay. And so you go, well, why would I do that? I mean, it's all I'm doing is increasing the entropy of the universe. You go, no. So your mom says, no, you're making the bed. Everything's ordered now. You know where things are. But really, when you're doing that, think about it. If you are burning calories, you're running the vacuum cleaner, you're ironing clothes. All of this is putting out energy into the room, heating up the room, heating up the molecules, making them go bounce faster and more chaotic. And so, yes, you might have brought order to what you visually see, but the invisible is much worse off. So the point is that you cannot, no matter what you do, you cannot, especially in the whole universe, you cannot lower entropy. Now, there's one way you could, and that's something called the Big Crunch. The Big Bang is where the universe came from. That's sort of the going theme right now, is the Big Bang. So everything came out of this infinitely small, which space-time, and then it all exploded. Not really, it wasn't, you couldn't hear it because there wasn't sound, but it all comes out. There wasn't light either, by the way. But so it all, eventually, so space-time grows. Well, that makes sense that since it's all growing, it's all getting more dispersed and more. So what's leading that is something called dark energy. And that's what, we don't understand dark energy very well, but we know it's the great, to me, it's a horrible description. It should just be called I had a name for it, the separator, the great separator. It just separates everything. And then the idea on this, when I was in high school in the 70s, the idea was that the gravity was going to win out, and then the whole thing was going to eventually come back together. And that's called the Big Crunch. So the whole universe would come back together. But then understand that if that happens, then the entropy switches and things become less chaotic and more ordered over time. And so they say, well, time in that case has to go backwards, because time is defined as a measure of the increasing amount of disorder of the universe. So if the disorder of the universe is decreasing, then time is then negative. You see what I'm saying? Okay. So that was in favor, but then this idea of negative time, it's just hard to get your mind around, and things become more organized over time. That's bizarre. And so that sort of died off, that idea. And now we say the ultimate theory right now is the universe ends in what's called a heat death. And that's fun. So everything ends in a heat death, meaning that dark energy wins and all particles are ultimately separated, meaning your left arm from your right arm, and then your particles in your arm, the molecules, then the atoms, then inside the atom, the electrons, the protons, the neutrons, then inside the proton, the quarks. So nothing is done until all things are as far apart as they can be. Then that's it. That's the end. So that's called a heat death. Okay. So we got into this discussion in second hour, a little bit in third hour. So I thought I would continue it here. It's kind of hard in this situation because I can't see your reactions. Okay. So for all I know, you fell asleep. All right. So that's probably good for today. We'll leave on that happy note of a heat death. Yeah. We got that to look forward to. But we're talking, I don't know, 5-6 trillion years from now. Not much to worry about tomorrow. Okay, let me stop sharing. All right, so we're good. Start working on that take-home test. Either print it off tonight or wait till tomorrow, come by and get it. And then come check out your test 2A. And then remember, tomorrow whoa, tomorrow's Wednesday. Okay, so tomorrow we're not gonna, if you get on here at 4, you're not gonna see me. I guess I could do it from my bike, but that probably wouldn't work. So we'll do it from 9 to 10. Did I say that? 9 to 10 tomorrow night. Late night Zoom. Okay, good. Anybody got anything to say before we go? I want to thank you all for coming. You're the best. And think about this next semester thing. Whoa, don't leave. All right, so here's what I want you to do. Either in the chat right now, or you can text me, then let me know what hour, like they're talking about making a virtual hour just for you guys. So what hour could you not do? No. What hour or hours would you prefer? 5th, 6th, or 7th? 5th, 6th, or 7th. Like if you're in Aegis and that meets right during the 5th, and you can't do 5th. Or if you're in AP, you know, Spanish or whatever it is, and it only meets a certain hour, you can't really do that hour. So maybe in the chat right now, you can just put down the hours you like. And if not, you know, think about it, then text me. Okay, so Io says it works better for him 7th hour. 5th, 6th, okay, good. It looks like 5th, well, it's a 6th or 7th. People don't like him 5th too much. Eric likes 5th. I should have asked, oh, good question, Jacob. You can just wait till you turn it in. You'll be back next week, eh? You're out for this week, but you can, hey, if you want to turn your paper in, that's fine. You can submit it if you want. It doesn't hurt. I'll see it again when I look at your packet. Okay, so it looks like people are liking 6th or 7th. Yeah, I know. You think you'll be back, right? I mean, who knows with this stuff. Okay, so 5th hour because of my schedule. I'd hate to lose Eric. Okay. Well, the upshot for me is that I'd actually get paid. Right now, I'm not getting paid for this. I mean, I'm enjoying you guys, but I'm not getting paid. So it'd be kind of nice if I got paid. So if it's, I might be able to say, well, let's make it 8th hour. Like it is, this is kind of like 8th hour, isn't it? I mean, 4 to 5. But a lot of people only get like 6 or 7 of you showing up, and I got 25 of you. So, you know what I'm saying? Yeah, so if you want to write me some more information on that, you can text it to me and I'll collect those, or you can email me, or you can message me on Facebook. Okay. Oh, okay. Eric says 7th hour would work. I don't mind. I don't mind any of them. I can work around the schedule. Whatever works. The more if I can get more of you, I will move. I will move the time if it allows more students to come, because you all do a lot better than those that just watch the recording or don't watch the recording. Okay, everybody, I'll let you go. Well, I'm gonna lose this chat if I kill it. Okay, so I'm just getting a gander here. It looks like mostly 6th or 7th seems to be the prevailing idea here. Yeah, Takaki, yeah, he says, well, none of my lectures do this, so he could work it in any time. That's probably true. I thought about, you know, having it in the morning, but then that doesn't work because some of you have physics, some of you have my 1st hour, some of my 2nd hour, some of my 3rd. I'm not doing it 3 times. And then you're recording the class, then you can't hear me, and then there's ambient noise, and then the camera's not right, and that doesn't work. All right, guys, I'll see you all tomorrow, late night, 9 o'clock. Come in your jammies. All right, bye-bye.